All right, so here's the plan today. What do you think, fella? Think we're ready to do calculus? He doesn't like to be on screen. Okay. But he's right in my face, just so you know. This entire time, he's right in my face. All right. Yeah, so now, guess what? We get to do integration. Won't that be fun? All right, so we're going to come back to our favorite three-petaled rows. What do I do with the rows? Okay, here we go. This guy. Remember this guy that we started out with? Yeah, I like to just take the same equation and just do lots of different things to it. So this time my question is, how much area do you think is contained in this first lobe? How much area? I mean, assuming I had drawn it correctly. How much area do you think that contains? That's our question. And by the way, all the three lobes are symmetrical, right? So I can do any of the lobes. They're all going to be the same. All right. So the idea that we need, first we need an idea of just how to even do that, because, you know, like if I try to build rectangles in here, it's not going to work because this shape is not rectangular. So what you build instead, I guess I could try to do it on here. I don't know if I'm going to regret this. Cat, get out of the way. Go on, fella. I'm just gonna draw it on this separate paper. So you can have any function, you know, looking like anything. So any kind of function, and then here's our origin over here, right? So, and I have r of theta, a function out here. So what I'm gonna do is, instead of drawing rectangles, you know, like what kind of shape can we fit in here, is we can fit in sectors. Right, so they're parts of a circle that go all the way back to the origin. So I have my sectors touching on the left side, so you could call it sort of a left-hand sector estimate. We're not going to have to actually do these, though. We're going to go straight to the integral on it. You'll be happy to know. But this is basically what it's going to look like. These are what the little sectors are going to look like in there. And we're basically going to fill it up with infinitely many sectors. I made that one a little large, but okay, maybe my delta x is not constant. All right. They also should all be going back to the origin. I sort of got lost over there. They should all be going back to the origin. Touching on the left side. Okay, so that's basically it, all right? And then, so what you have to do is say, you know, what's the area of the ith element? You know, what is the area of each of these sectors? All right, well, what's the area of a sector in general? So if I have a sector, and it has an angle theta, and it has a radius r. Well, I know that the area, if I had the whole circle, would be pi r squared, and this is a fraction of the circle. It's theta over 2 pi of the entire circle, right? So the area is theta over 2 pi times the area of the circle, which is pi r squared. Then it happens that the pi's cancel out, so you have 1/2 r squared theta. You may have learned that formula for the area of a sector either in geometry or in pre-calculus when you do some kind of like arcs and things. You can do some kind of, what do they call it, rotational dynamics or some such. Anyway, 1/2 r squared theta. So that means that our ith volume element is going to be 1/2 r. Now remember, the r depends on theta, so it's going to depend on an ith theta squared. And then what's going to happen to the theta? What's the width theta of each of these? Well, instead of a delta x or a delta y, I have delta theta, just like we used for graphing, right? The width of each of these is delta theta. I'm using width in quotes. It's not really width. So it's an angle. So the a sub I is 1/2 r of theta sub I squared delta theta. That means that we can, you know, once you know what the ith element is, you can take a limit as n approaches infinity and get the area is equal to 1/2 the integral from a to b of r of theta squared d theta. So as usual, the delta theta becomes d theta. And then you just have that nice easy formula. That's just it. I think what I decided to do is just go ahead and throw in, you know, we want to do area between two curves sometimes. So what if I had another curve down here that was bounding the inside of that shape, right? Then I would have so this is a simple shape. Then for a complex shape involving two curves, it's pretty easy to just generalize and say you're going to have 1/2 integral from a to b of r2 squared well, let's go ahead and put r2 of theta squared minus r1 of theta squared d theta. So the r2 and r1 are playing the roles of g and f, and as usual, we're going to do the inner function minus the outer function. So if this were two different functions, I would do the integral 1/2 times the integral from a to b of this outside function squared minus this inside function squared, and that's really all there is to it. So we're going to look at some examples, but this is the whole deal right here. And most of the integrals that we're going to get are not possible really to evaluate. I mean, there are ways to evaluate some of them by hand, a lot of them not so much. But let's go ahead and do one lobe of r equals 7 sine of 3 theta. We'll see some of the kind of different considerations that come up. So if I'm going to do one lobe, or we could call it a petal. Some people call it a lobe. Petal's prettier, I guess. 7, so unless you have really pretty ears, then lobe might be pretty. All right, so one thing that's going to be always a problem is what are the a and the b. So, you know, in this formula, so a and b are the limits on theta. The limits are theta. So you have to think, what is the value of theta that I'm starting at, and what is the value of theta that I'm ending up at? This is theta equals a and theta equals b. So that's going to be a big part of the trick. So how do we know, looking at this graph, for what value of theta is this lobe? What values of theta are covered by that? Well, it's a pretty good guess that 0 is the starting point. We did some analysis last time. We found out that the maximum had to be pi over 6. So that means that when we come back down, assuming everything's symmetrical, which it is, we have to be coming down at pi over 3. So it's 0 to pi over 3. Okay, but ways that you can sort of analyze that better if you didn't have as much information. You think, this is sine of 3 theta, right? And I want to know, what is the first time we go from 0 to 0? Well, how does sine of theta go from 0 to 0? Sine of theta starts at 0, goes up and then comes down to 0, and does that from 0 to pi. So what has to happen is that our argument of sine, that's what that's called, the inside is called the argument, is 3 theta. That has to be between 0 and pi. So that can give you also that 0 is less than or equal to theta is less than or equal to pi over 3. So that's how we can figure out that that first lobe, like this is what we really need, is to know that theta is going from 0 to pi over 3. And those kind of considerations are often not obvious. You have to like really think about the graph to get what those limits are going to be. But then once you get it, the equation is easy because you just do area equals 1/2 the integral from 0 to pi over 3 of 7 sine of 3 theta squared d theta. Now, it is possible to do this by hand. Some people in the volume section apparently went and looked up how to do integral of sine squared using double angle formula. That's very cool. It's technically not part of our curriculum, so you definitely do not have to do that. You would just throw this in your calculator. So all these integrals that we're going to get, just throw them in your calculator so that I don't have to worry about whether they're doable or not. It turns out to be 12.828. Don't forget the 1/2, like I did a couple of times. All right, so the area of that lobe is 12.38. Kind of makes sense a little bit, like if you think a rectangle that is, like this length is 7. So I've had a rectangle that was 7 by 2. That would be 14. And this lobe, because it gets really skinny, is less than 14, a little less than 14. So I mean, it kind of makes a little sense, but that kind of analysis is very estimating. All right, that's your basic area. We're going to do some more areas next. Yeah.